Yesterday when we introduced our new unit, the first term we defined was a magnetic domain. Anybody tell me what that is? Context of magnetism, what's a domain? You don't need to give me the details about the subatomic structure of it, right? Electrons and all that kind of stuff. Give me the gist of it. Give me the working definition of a magnetic domain. We talked about what we call ferromagnetic materials yesterday, and we said a ferromagnetic material is a material that has the potential to become magnetized. And these ferromagnetic materials have these tiny little regions called domains inside them. And these regions that we call domains really have to do with patterns of electron spins, but what we really care about is that they're just regions inside, and that we represent these regions by arrows. Now, normally, in a ferromagnetic material, we've got all these domains, but they're pointing in random directions. In order to become a magnet, we need to cause them to point in the same direction, or in a similar direction at least. And there's a couple ways that we can do that. What's one of the ways that we can cause these domains to point in a similar direction? Yep. Yeah, put it near a permanent magnet. That can literally be another bar magnet or whatever magnet that has its domains aligned already. Or it could be something as simple as the Earth. Do you know that most buildings now, high buildings, are made primarily of steel, right? They're steel frame buildings. There's concrete in them, and then the rest of it is basically window dressing, right? Okay, mainly steel. That's the structure of the building. That's what supports the building. Steel is an alloy that contains iron. Steel is a ferromagnetic material. Steel has the potential to become magnetized. Older buildings that are made out of steel have been found to actually be magnetized, and they're magnetized by the Earth's magnetic field. Now, it takes a long time to magnetize the steel in a building by the Earth because the Earth's magnetic field is so weak, right? 10 to the minus 5 Tesla versus 10 to the minus 2 Tesla for a bar magnet. But still, over a period of time, the Earth's magnetic field acts as that permanent magnet, which will essentially induce a magnetic field, a temporary magnetic field in a piece of steel. What's the other way we can cause the magnetic domains in this non-magnetized ferromagnetic material to become aligned? Yep. Good, you said it perfectly. Sometimes when I ask that question, I hear the answer, run a current through it. We don't want to run a current through it. Okay, that's not going to cause the domains to become aligned running a current through it. Running a current through a wire causes a magnetic field, and that magnetic field will cause the domains in this ferromagnetic material to become aligned. We're going to talk more about that today. Okay, that's basically the gist of the lesson today, is this whole idea of electric currents generating the magnetic field. All right, we talked about 3 laws of magnetism as well, 3 laws that were real similar to the 3 laws of electricity. What's the first one? Any order. Hey, I shouldn't say what's the first one. What's one of them? Yep, Chase. Like poles repel each other. Remember, we're not talking about like charges, so we're not talking about positive repelling positive. It's true, positive does repel positive, but that's a whole different law. That's a law of electricity. Like poles repel, north repels north, south repels south. Second law, or one of the other 2 laws? Yeah, unlike poles attract. So we're talking about now, again, North Pole, South Pole, as opposed to positive and negative. Positive does attract negative, but what we're talking about here is north attracting south, or south attracting north. And the third one, this one's a little bit further away from the 3rd law of electricity, but it still has similarities. Charged objects attract neutral objects for the electrical law. Yeah.
Magnetized objects attract ferromagnetic.
Yeah, yeah. Magnets basically attract non-magnetized ferromagnetic materials. It's got to be ferromagnetic because you put a magnet nearby your desk, it doesn't attract the top of your desk. But if you put it near the leg of your desk, it does attract the leg of your desk, right? They're both not magnetized, but they both have, the leg of your desk has the potential to become magnetized. And why does it do that? It's because of induction. It's a different kind of induction. It's not electrical induction, but this is our our non-magnetized ferromagnetic material with domains pointing in random directions, and we bring that magnet nearby, what happens? Well, it causes the domains in the non-magnetized material to temporarily align like this. It induces a temporary alignment of domains. Just like, remember, with charges, it induced a temporary separation of charges. Well, because these domains are aligned, look, this is going to attract this because they're pointing in the same direction, right? We could pretend to join them together there, and if they join together, they're going to attract. So we say that the magnet attracts the non-magnetized object, which is true, but I guess you could also say that the non-magnetized object isn't non-magnetized anymore, right? It becomes a temporary magnet, and ultimately that's why it's attracting, is because the non-magnetized thing becomes a temporary magnet as it's brought nearby another magnet. All right, a couple more things before we move on to some new stuff here. Yesterday we defined the direction of the electric field in two ways. The first way was, think about electricity again, it was the way that a positive charge would experience a force in the field. Magnetism, it's the way that, nothing to do with positive charge now, right? It's the way that a compass needle would move if placed in the field. And of course, the second way is, which way does a compass needle point? Remember, we're talking about a compass needle, talking about the north end of a compass needle. A compass needle is really a magnet with a north end and a south end. But the end that we look at is the north end. So which way is the north end of a compass going to be attracted to? Which end is it going to be pulled towards? Right. So the magnetic field would go from north to south, just like an electric field would go from positive to negative. And that creates a whole lot of issues. I mean, it's purely arbitrary definition, understand that, right? Like we could define it the other way around, okay? The way that the south pole of a compass points, right, is the direction of the magnetic field from south to north, but we don't, okay? It is what it is. But that definition creates a whole lot of issues, including an apparent contradiction with the Earth's magnetic field. Okay. We know that the Earth generates its own magnetic field, and it's like the magnetic field surrounding a bar magnet. It goes like this. But we know that that magnetic field goes this way, because that's the way the compass needle points, right? Towards the North Pole. But we also know that it goes toward the south. That means that seems like there's a problem with the definition here, because we get a south pole up where we think of it as being the North Pole. The reality is it's a bit confusing, because we've got our poles reversed to what we're used to calling it. But if we get past that, if we get past that whole idea that it has to be called this, really we can call it whatever we want, right? Okay. And in the end, we're saying that this is the South Pole, magnetic South Pole, fundamentally because of the definition of the direction of magnetic field. Geographically, it's still north. Magnetically, it's south. That's why compasses point that way, right? If you don't believe me, literally you could take, and we're not going to do this, but you could literally take a bar magnet, a pretty commonly available bar magnet, hang it from a little string, okay, make sure it's balanced so that it's, gravity's not affecting it that much. Make sure it's balanced, hold it, and the north end of that bar magnet will point that way towards Calgary. Why would the north end point that way? Because the north end is attracted to the south, magnetic south. Okay? All right. All right, I want to draw a few pictures here right now, different scenarios of bar magnets. And as opposed to drawing the field lines, having you draw the field lines or predict what the field lines are going to look like, we're going to kind of work backwards today. Yesterday, I showed you the magnets. You measured the direction of the magnetic field surrounding those magnets. Today, I'm going to draw magnets in different scenarios, and I want you to make predictions as to things like polarity of the magnet, direction of field, and so on. First one we're going to draw is this. Okay, I'm going to draw one field line pointing this way. I want you to tell me what the polarity of that bar magnet is. Left side, north or south? Right here. How do you know? Who said that? Chase? How do you know? Sorry? Good. The magnetic field goes from north to south. That means this one has to be north as well. Hey, what if I had just drawn something like this? What if I didn't even draw the field lines in there and I just labeled this as south? What end does that have to be? Could it be a south? I mean, clearly it could be a north, right? Could it be a south? No, you can't have what's called a magnetic monopole. Okay, if you've got a pole, you have to have two of them. If you have a north, you have to have a south. If you have a south, you have to have a north. That's not like electricity, right? Electricity, you can have a single positive charge. In magnetism, you can't have a single pole. It's got to be a north and a south. Look, domains point in one direction. They go from south to north. If they go from south to north, you can't take this and say it's a south because they're pointing toward the north. By definition, you have to have a south pole and a north pole. If you ever figure out a way to have just a south pole or just a north pole, you should tell me. And then when I win the $1 million for the Nobel Prize in physics, I'll share it with you. I'll take the credit, but I'll share the prize with you. I mean, it's a big deal, right? I mean, bottom line is, you can't have, as far as we know, you can't have just a north pole or just a south pole. So if you got one labeled south, the other one has to be labeled north in every single circumstance. All right, let's draw another one here. And then I will come back to your question in just a couple minutes here, okay? Here's another scenario where we got two magnets like this. What do you know, first of all, without even looking at the direction of the field lines there, what do you know about these two poles right here in those two positions? You can't give me specifics, but you can tell me in general they must be like poles. And how do you know they got to be like poles? Yeah, if the field lines join up, we've got to have attraction. If the field lines don't join up, we've got to have repulsion. That's like electric fields, right? If they don't join up, it's got to be repulsion. If it's repulsion, then they've got to be like poles. Now, what is it? North and north or south and south? How can we tell? Peyton? Why do you say, Peyton, it's north and north? Good. We've got one single field line drawn here, and it's going away from this pole. Therefore, that's got to be a north pole. The field lines go away from north. And they go toward the south. Well, we don't have the rest of them drawn, but now we could, now that we recognize that that's a south pole. Does that make sense? Huh? Okay, let's try just a couple more diagrams here. What do you know about these two poles? Jonathan? They got to be opposite poles. Now, we don't have enough information to say what they are, north and south or south and north, but we know they've got to be opposite. The field lines join up, therefore they've got to attract each other. All right, let's say that I labeled this one as a south. Okay, what's this one got to be? Got to be a north, right? What's this one got to be? Got to be a south. This one's got to be a north. Which way do the field lines go? From north to south. So we can, with just one little thing labeled and the drawing or the shape drawn in, we can label a whole lot of other things, 3 other poles in the direction of the field. One more picture here. This one's going to look a little bit different than one you've seen before, but you can still nail this one. Should have picked a different color here, I guess. Kind of looks like a Big Mac patty and These are supposed to be field lines right here. Okay. And these are supposed to be my magnets right here. What do you know about these two magnets, first of all? Going to attract or repel? Yep. They're going to be repelling. And how do you know that? Yeah, the field lines aren't joining up, right? If they were attracting, these field lines would join up like this. So it's repulsion. So that means that this pole is going to be the same as this pole, and this pole is going to be the same as this pole, right? Now, we don't have any directions labeled there. If we label one single direction, then that means we have enough to label the rest of the poles, right? This one has to be south because it goes toward the south. This has got to be north. And then therefore, because this repels, this has to be north, and this has to be south. So even if you see a scenario that we didn't do yesterday, you can still use the reasoning that we used yesterday in order to figure out what's what, right? So we got a question here now from the audience. It says, basically, if you didn't hear, north and south poles both attract not neutral, I was going to say neutral objects. North and south poles both attract non-magnetized ferromagnetic materials. Okay. Why would that be the case, basically? Why would both of them attract non-magnetized as opposed to just one of them attracting non-magnetized? Is that right? Okay, so let's take our non-magnetized ferromagnetic material. They got domains pointing in every which direction, right? Random directions, right? Let's take a magnetized object with a north pole and a south pole like this. Okay, that means the magnetic domains inside that are going to point from south to north, right? That's going to influence the domains in the non-magnetized thing to point in the same direction. Okay, by induction, we induce these domains to point in this direction. Now, because these domains are pointing in the same direction, there's going to be a force of attraction between this thing that was non-magnetized, but now really isn't. Now it's really magnetized. Okay, there's going to be a force of attraction here. This would be the south end, this would be the north end, right? But if I reverse that, if I had my non-magnetized ferromagnetic material with random domains right next to a magnet with the poles opposite to that, south pole and north pole, look, we got our domains inside that one going from south to north. That's going to cause these domains to point in the same direction like this, which is going to mean this becomes a north temporarily, this becomes a south temporarily, and all of a sudden now we're going to get attraction again. Does that make sense?
So what's the magnetic field have that equal again?
What significance does the magnetic field have?
I understand, like batteries want to have current, electricity going that way.
Yeah. In a sense it is, yeah. No, in a sense it is. I mean, the whole idea of fields, whether it be gravitational electric fields or magnetic fields, are human-made constructs. We use them to help us to see the influence of things when there's nothing to be influenced. Okay, let me go back to gravity for a second because that's a little bit easier for us to see because we experience that more, right? Okay, I got a board marker in my hand right now. It experiences a gravitational force. We have no problem describing gravity, okay, when there's a board marker experiencing a force. But when I take that board marker away, it doesn't mean that gravity has disappeared, right? The thing that caused gravity is still there. And if the thing that's causing it hasn't disappeared, then it's got to be there still, right? But how do we describe it if there's nothing to feel it, nothing to experience it? That's the whole idea of the field. That's where we introduce the idea of the field. Same kind of idea with electricity and magnetism as well. Okay, there's an influence that surrounds this magnet. Okay, and there's going to be an influence here whether there's something there to experience it or not. There's going to be an influence here whether there's something to experience it or not. It's just that right now we have something to experience it. Does that make sense? Okay, over here, same kind of deal, except the field's going to be reversed. And going from north to south. Notice the domains go south to north. The fields go north to south. They just kind of continue the circle there. It's not flowing. It's just an area of influence. Okay, the field here would go this way, caused by this, but that field, ultimately, it's that field that influences these domains to cause them to point in that direction. Okay?